No matter what device you're using right now, a phone, a laptop, anything with a screen, you are relying on billions of tiny, invisible, one-way streets for electricity. We call them diodes, and they are the unsung gatekeepers of all modern electronics. So how on earth do they work?
If you ever crack open a circuit diagram, you are going to see this symbol everywhere, a simple little triangle pointing at a line. This is the diode. And trust me, that arrow isn't just there to look pretty, it's the key to its one and only job. So what's the secret here? How can this tiny, solid component with absolutely no moving parts act like a perfect one-way valve for electricity? How does it know to let current flow with the arrow but slam the door shut if it tries to go the other way? Well, let's dive in and find out.
Okay, our story starts by forging something called PN Junction. This is the heart of the diode. It's where we take two very different types of semiconductor material and bring them together to create something totally new. It all begins with these two special materials. On one side, we have P-type semiconductor. Think P for positive. It's full of these little empty parking spots for electrons that we call holes. On the other side, we have N-type for negative, and it's packed with free-roaming electrons. You see where this is going? Each one has exactly what the other one wants.
The second these two materials touch, a few things happen in a flash. First, diffusion. All those free electrons from the N side rush over to fill the empty holes on the P side. Next, recombination. Right where they meet at the junction, they pair up, neutralizing each other. This whole thing happens incredibly fast until, finally, it reaches equilibrium and everything just settles down. But that brief moment of chaos has a permanent consequence. In that tiny sliver of space where all the action happened, a barrier has been created. It's like an electrical wall built right in the middle of our material. And this wall has a name, the depletion region. It's called that because it's been completely emptied or depleted of any charges that can move freely. What we've basically done is create a tiny sliver of an insulator right between our two conductors. It's a true no man's land for electricity. So let's break down exactly how this wall gets built. Remember, the N region lost a bunch of negative electrons, which means it's left with a net positive charge, and the P region gained those electrons, giving it a net negative charge. This separation of charge across that depletion region creates a built-in electric field, and we call that the barrier potential. A really great way to visualize this barrier potential is to think of it as an energy landscape. See, for an electron to get from one side to the other, it's not a flat path anymore. It now has to climb a steep energy hill. In this diagram right here, it shows us exactly what's going on. On the left, when the materials first meet, the energy path is totally flat. But look at the right. Once equilibrium is reached, that barrier potential has created a steep energy hill right at the junction. And this hill now physically blocks any more electrons from just wandering across on their own. So you might be asking, why is the N side a lower energy level for an electron? Well, it all comes down to basic physics. The N region lost electrons, so it became positively charged. And since electrons are negative, they're attracted to that positive region. It's like rolling downhill into a valley. The P region, on the other hand, became negative, which repels electrons, creating a higher energy state they have to climb out of. That difference in energy is the hill. Okay, so we've built this awesome, very effective wall, but a diode needs to be a controllable valve. And the way we control it is by applying an external voltage. It's a process we call biasing, and it's how we open and close the gate whenever we want. First up, let's look at the default state, no bias. This is what the diode is doing when it's just sitting there in a circuit, with no power connected to it. So, without any external voltage pushing things around, the diode is just chilling. That depletion region is stable, the energy hill is firmly in place, and absolutely zero current is flowing. Yep, the valve is shut tight, the diode is in its default off state. Simple as that. All right, now for the fun part. Let's turn it on. We do this with what's called forward bias. This is how we open the floodgates and let the current flow. And how do we do it? We just connect a power source, positive to the P side and negative to the N side. This external voltage literally shoves the holes and electrons towards the junction, giving them just enough energy to overcome that barrier. And as a result, the depletion region shrinks and boom, current flows freely. So think of it this way. Forward bias gives the charges the push they need to get over that energy hill. By applying this voltage, we effectively flatten the hill, shrink the depletion layer right down, and flip the switch to on. But what happens if we hook up the battery the other way around? Well, that's called reverse bias, and it's how we basically double bolt the door to make sure it stays off. By applying a negative voltage to the P side and a positive one to the N side, we do the exact opposite of what we did before. We literally pull the holes and electrons away from the junction. This makes the depletion region even wider and that energy hill even taller, strengthening the barrier and ensuring practically no current can get through. So let's tie all of this back to that simple little arrow we started with, because after everything we've just seen, it's finally going to make perfect sense. See, it all clicks into place now. The flat side of the arrow, the anode, that's our P-type material. The line it's pointing at, the cathode, that's our N-type. And the arrow itself points in the direction of conventional current, from positive to negative. It's a literal signpost showing the one direction traffic is allowed. And after all that physics, all that talk of junctions and barriers and energy hills, it all comes down to this one beautifully simple, powerful function. By creating a barrier and then giving us the tools to either shrink it or grow it, the diode achieves its purpose. It allows current to flow in one direction only. And this simple one-way street isn't just a component. It's a cornerstone of our entire digital world. Think about it. The power from your wall flows back and forth, but your phone needs steady, direct power. The diode makes that conversion possible. It's the foundation for transistors, for microchips, for everything. So the real question is, once you can control the very direction of electricity, what can't you build?